going to derive the formula for the circumference of the circle. So let's formally state it, and then we'll prove it. Given a circle of radius r, the circumference is 2 pi times r. Now, there's a few things that I want to prove first, or talk about first. One of them is that if you have, say, a circle centered at the origin, well, it's a radius r, it's going to have some arc length or some circumference. Now, if you were to move this circle over here, try my best to draw the same exact circle, but you move it. Maybe you have a poker chip, or I'm thinking of not chess, a checker piece. If you have a checker piece which is filled in, it's solid, but we can think, and you know, it's three-dimensional, it's in thickness, but let's just talk about the top coating. Okay, now this is the circumference all the way around. Now, if you move the piece, which you generally do in checkers, it's still going to have the same circumference. And if you move it later, it's still going to have the same circumference. So, without loss of generality, I'm going to prove that if the circle is centered at the origin, that the circumference will be 2 pi r. Okay, so let's get on to this. So, proof. The equation of a circle centered at the origin, 0, 0, is x squared plus y squared equals y squared. Now, another thing I want to point out is if I draw my axis and that's the dead center of the circle, since the circle is symmetric, this distance is going to be the same. That arc length is going to be the same as this arc length, which is going to be the same as that arc length, which is going to be the same as this arc length. So, if I just find this arc length, just the one in the first quadrant, and I multiply it by 4, I will be done. So, here is our circle. And again, we only want to find this arc length, this piece. R, negative R, negative R. Oops. Y-axis, x-axis. Now, what I can tell you about all of these points along that portion of the curve is y is always positive. So I want to solve for plus y squared. So y squared is r squared minus x squared. So y is plus or minus the square root of r squared minus x squared. But I only want y to be positive. So I can get rid of the minus. So that's the equation of this. That's the equation of this, even with the constraint that x is positive. With the added constraint x is positive. Because this equation right here just happens to be the equation of the top half. But I only want to talk about when x goes from 0 to r. Only about the first quadrant. So what we have is this. The arc length, which I'll call S, is going to be 4 times the arc length of the arc in the first quadrant. I'm going to calculate the arc in the first quadrant using an interval. It's going to be 1 plus dy dx squared square root times dx. And x is going to go from 0 to r. Well, I know where 1 is. I know where plus is. Now, I need to find out what dy dx is. So we'll do that right here. In fact, let's find out where 1 plus dy dx is. Well, y is equal to the square root of x squared minus y squared. And I'm going to realize the square root as a half power. So if you have a function to an integer, to a constant power, you use the general power rule. You keep the function the same. Just like when it was x. You bring down the power, you make the new power 1 less, which is negative 1/2. Make the new power 1 less. Then you don't forget to take the derivative of what's in there, which is negative 2x. First thing I would say is the 2's cancel. So I have negative x times 1, which is negative x, and this piece here. But since it has a negative exponent, I'm going to put it in the bottom. So it's going to become r squared minus x squared to the half. That is square root. Now, if I square that, because that's what I need in my formula, I get negative x squared, which is x squared, and the square root of r squared minus x squared is just r squared minus x. But I don't even want that, ultimately. I want 1 plus that. So since the second value, or term, is a fraction, I'm going to write the 1 using that fraction, that denominator, as x squared, r squared minus x squared over r squared minus x squared plus the second term. And since they have the same denominator and we're adding, I keep that denominator. And I add the tops. R squared minus x squared, but then we add back there x squared is just r squared. Okay. One last thing. The square root of 1 plus y prime squared is the square root of that, which is equal to the square root of this, which is the square root of that. And I guess I can say one last thing. The square root of r squared, since r is positive, the radius can't be negative, is r. All over r squared minus x squared. So I found out exactly what 1 plus the derivative squared square root is. So this gives me 4 times the integral from 0 to r. Here's my dx. And this whole piece, I worked out. It is this. It is r over the square root of r squared minus x squared. Okay. Now, the first thing I would do is factor out the r. So it's 4 into 4r, 0 to r, dx over r squared minus x squared. Now, let me get rid of all of this side work. No longer needed. Get rid of all of it. Okay. Oops, I have that typo. It clearly says square root. So whenever you have r squared minus x squared or r squared plus x squared or x squared minus r squared, whether it has a square root or not, use trig substitution. r squared minus x squared. The r squared is a positive term. Put the positive term, the square root of the positive term, on the hypotenuse. Don't worry about plus or minus. The minus x squared, the square root of that is x, put that on one of the legs. And then the square root goes on another leg. So I need two pieces. I need to know how to write dx in terms of u, and I have to know how to write the square root of r squared minus x squared in terms of u. Well, if I had x equal, then the differential of the left side will be x, dx, which is what I want. So I like to find a nice trig function that has x and a constant, no more x's. Well, it turns out that the sine of u is the opposite, x, divided by the hypotenuse, which is r. Instead of dividing by r, I'll multiply the other side by r. This way, I just have x, and finding the differential is easy. Plus, I already have one side being dx. So, I have dx. Now, I need to get something that talks about r squared minus x squared. And if I can get it as the square root right away, wonderful. Oh, look at this. It's right here. I would love to find a trig function that divides those two. No more x's. Well, it turns out that the cosine of u is the adjacent, which is what I want, divided by r. Well, I just want this. Instead of dividing by r, I'll multiply the other side by r. So now, we have the for r, the integral, dx is on top, which is r cosine u du. In the bottom, I have the square root of r squared minus x squared, which is r cosine u, which is really nice because everything cancels out. And basically, let's just jump on it. We have 4r, the integral of du. But what are the limits? We know that our substitution is x is equal to r sine of u. And u goes from, x goes from 0 to r. So, when x equals 0, what does u equal? And when x equals r, what does u equal? Well, if x is 0, that means this is 0. It turns out that the sine of u is 0 at 0. It's 0. Now, when x is r, that means this equals r. Well, r times this is r. This must be 1. That happens at pi over 2. So u is pi over 2. So we go from 0 to pi over 2. And there's the 4r. The integral of du is simple. It's just u. And u goes from 0 to pi over 2. So you get 4r times u minus 4r times 0. And of course, 4r times 0 is 0. And 2 goes into 4 2 times. So we get 2r pi, which is the same as 2 pi r. So now we know for sure that our teachers haven't been lying to us. The arc length of a whole circle, the circumference of their entire circle is 2 pi r. Pretty neat.